Real numbers. A real number is any number that can be found on the number line. These are the numbers that we normally use and apply in real-world applications. Let us understand the types of real numbers. Natural numbers are 1, 2, 3, etc. Whole numbers start from 0 and includes all natural numbers. Negative integers are -1, -2, -3, etc. Integers includes 0 and positive and negative integers. Fractions are of the type 8 upon -5, -1 by 3, 1 by 2, 5 upon 2, etc. Irrational numbers, the numbers whose decimal representation is non-terminatory, non-recurring, are called irrational numbers. Euclid's division algorithm is a method to find the HCF of two integers. It states that any positive integer, a, can be divided by another positive integer, b, in such a way that it leaves a remainder r that is smaller than b. Let us take this real-life example to understand the algorithm better. A trader was selling eggs along a road. An idler provoked the trader into a wordy duel. This grew into a fight. Due to this, the eggs were broken. The trader requested the panchayat to ask the idler to pay for the broken eggs. The panchayat asked the trader how many eggs were broken. He gave the following response. If counted in pairs, 1 will remain. If counted in threes, 2 will remain. If counted in fours, 3 will remain. If counted in fives, 4 will remain. If counted in sixes, 5 will remain. If counted in sevens, nothing will remain. My basket cannot accommodate more than 150 eggs. Let us try and solve the puzzle. Let the number of eggs be A, then working backwards, we see that A is less than or equal to 150. If counted in sevens, nothing will remain, which translates to A is equal to 7p plus 0 for some natural number p. If counted in sixes, 5 will remain, that is A is equal to 6q plus 5 for some natural number q. If counted in fives, 4 will remain, giving A is equal to 5w plus 4 for some natural number w. If counted in fours, 3 will remain, that is A is equal to 4s plus 3 for some natural number s. If counted in threes, 2 will remain, that is A is equal to 3t plus 2 for some natural number t. If counted in pairs, 1 will remain, giving A is equal to 2u plus 1 for some natural number u. That is, in each case, we have A and a positive integer b. B takes values 7, 6, 5, 4, 3 and 2 respectively, which divides A and leaves the remainder r. In our case, r is 0, 5, 4, 3, 2 and 1 respectively. That is smaller than b. But this is a very long method, so we will learn Euclid's division lemma. Theorem 1. Euclid's division lemma. Given positive integers a and b, there exist unique integers q and r, satisfying a is equal to bq plus r, 0 less than equal to r less than b, to obtain the HCF of two positive integers, say c and d, with c greater than d. Follow the steps below. Step 1. Apply Euclid's division lemma to c and d. So we find whole numbers q and r such that c is equal to dq plus r, 0 less than equal to r less than d. Step 2. If r is equal to 0, d is the HCF of c and d. If r is not equal to 0, apply the division lemma to d and r. Step 3. Continue the process till the remainder is 0. The divisor at this stage will be the required HCF. Use Euclid's algorithm to find the HCF of 4052 and 12576. Solution. Step 1. Since 12,576 is greater than 4,052, we apply the division lemma to 12,576 and 4,052 to get 12,576 is equal to 4,052 into 3 plus 420. Step 2. Since the remainder 420 is not equal to 0, we apply the division lemma to 4,052 and 420 to get 4,052 is equal to 420 into 9 plus 272. Step 3. Again, the new remainder is not equal to 0. So the new divisor is 420 and the new remainder 272, and apply the division lemma to get 420 is equal to 272 into 1 plus 148. Repeating the same procedure until we get the remainder 0. The remainder has now become 0, so our procedure stops. Since the divisor at this stage is 4, the HCF of 12,576 and 4,052 is 4. Theorem 2. Fundamental theorem of arithmetic. Every composite number can be expressed, factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. We are going to use the factor tree with which you are all familiar. Let us take some large number, say 32,760, and factorize it as shown. 32,760 is equal to 1,380. Further, 16,380 is equal to 2 times 8,190. Next, 8,190 is equal to 2 times 4,095. Factorizing all the composite numbers in such a way, we get the prime factors of 32,760 is equal to 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. Let us take another example. Find the HCF of 96 and 404 by the prime factorization method, hence find the LCM. Solution. The prime factorization of 96 and 404 gives 96 is equal to 2 raised to 5 times 3, 404 is equal to 2 raised to 2 times 101. Therefore, the HCF of these two integers is 2 into 2 is equal to 4. Formula to find the LCM of any two positive integers a and b using LCM is LCM of AB is equal to A into B upon HCF of AB. Therefore, LCM of AB is equal to 96 into 404 upon 4, that is equal to 24 into 404 is equal to 9,696. Theorem 4. Prove that root 2 is irrational. Proof. Let us assume to the contrary that root 2 is rational. So we can find integers r and s not equal to 0 such that root 2 is equal to r upon s. Suppose r and s have a common factor other than 1. Then we divide by the common factor to get root 2 is equal to a by b, where a and b are co-prime. So b root 2 is equal to a. Squaring on both sides and rearranging, we get 2b squared is equal to a squared. Therefore, 2 divides a squared. Now, by theorem 3, it follows that 2 divides a, so we can write a is equal to 2c for some integer c. That is, b squared is equal to 2c squared. Therefore, a and b have at least 2 as a common factor. But this contradicts the fact that a and b have no common factors other than 1. This contradiction has arisen because of our incorrect assumption that root 2 is rational. So we conclude that root 2 is irrational. Theorem 5. Let x be a rational number whose decimal expansion terminates. then x can be expressed in the form p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n, m are non-negative integers. Theorem 6. Let x is equal to p upon q be a rational number such that the prime factorization of q is of the form 2 raised to n 5 raised to m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. For example, 1. 7 upon 80 is equal to 7 upon 2 raised to 4 into 5 raised to 1, multiplying both numerator and denominator by 5 raised to 3 to make the power of 5 as 4, which is equal to 875 upon 10 raised to 4, that is equal to 0.0875. 2. 14,588 upon 625 is equal to 2 squared into 7 into 521 upon 5 raised to 4 into 2 raised to 4 upon 2 raised to 4, that is equal to 23.3408. From these examples, we write the decimal expansion of such a rational number terminates.
Theorem 7.
Let x be equal to p by q be a rational number such that prime factorization of q is not of the form 2 raised to n upon 5 raised to m, where n and m are non-negative integers. Then x has a decimal expansion which is non-terminating, that is recurring. For example, 1 upon 7. We divide 1 by 7 since 1 is smaller than 7. We put a decimal in the quotient to make the 1 as 10. Therefore, 7 ones are 7. Remainder is 3. Again, we make 8 30. Then 7 fours are 28. Balance is 2. Then 7 twos are 14. Remainder is 6. We repeat the procedure until we again get 1 in the remainder, so that the numbers in the decimal again repeats itself. So we know that 1 upon 7 will not have a terminating decimal expansion. The remainders will start repeating after a certain stage. So we will have a block of digits, namely 1, 4, 2, 8, 5, 7, repeating in the quotient of 1 upon 7.